Good morning, everyone. Welcome to Outside. So the next upcoming assignment is going to be about planning a tour through the moons of first Kerbin and then flying out to the planet Jewel, which has more moons. And I mean, the second part is marked as being an extra point part, but it's sort of the full version of the assignment is going and doing the Julian tour. So in order to be able to deal with a tour, the kind of problem that we have is a sort of path planning or general planning or routing problem. These problems are all related, and this is a problem in sort of that category. Now, there's a couple of different traditional problems that fall in that category. For example, internet routing, where we're going to have packets get routed between different machines, is a routing problem. But it's the same sort of algorithms as path planning. And we're outside, so there's car noises and wind chimes. This is going to be a wonderful video. In any case, another common planning problem is just what Google Maps does, where you have a vehicle that you're going to be driving through some sort of maze or on some sort of roads or something, and you need to find an efficient path from the start to the finish. And efficient can be in time, it can be in fuel, it can be in a distance you could optimize for. And these are all like potentially different things that may produce different routes through the same map. Another traditional planning problem is the robot motion planning problem. And let me actually draw a picture on that one. So let's go ahead and figure out where the camera can actually see. So the camera can see here. If we have some sort of room and we have a robot, I'm going to double check that this can see my drawing. Yeah, it looks like it can see my drawing. This is a high-tech blackboard that was not funded by Northeastern, but it's a high-tech blackboard. So we have a robot here. The robot's facing that direction. We want the robot to be here, facing this direction. And the question is, what set of actuator commands do we need to do to get the robot from there to over here? And in order to find that, we have to do a search through the space of possible sequences of commands. So looking at this as a human, it's real straightforward. We drive the robot forward until it's there, and then we're going to rotate it until it's going to be pointing in that direction, and then we drive the robot backwards until it gets here. At least that's what we do if we can drive backwards. If we need to drive forwards the whole way, we drive forwards to here, turn this way, drive forwards this way, and then turn the robot all the way around. But that's if the robot is allowed to turn in place. If we have a car-shaped robot, this is the problem with this whiteboard, is that erasing is awful on it. If we have a car-shaped robot that has car steering, this becomes a slightly more annoying problem. So we have to try to drive the robot forward, and we probably want to try to sort of drive it into this corner. And then we want to back the robot up that way, and we have to figure out how to steer the robot so it's actually backing up properly. So this is one of the traditional robot motion planning problems, and this raises the question of sort of what kind of algorithm can we use to actually deal with this. And the standard algorithm to deal with all of these problems is a class of algorithms called graph search. So first we want to take whatever the concrete problem that we're talking about is, and we want to translate it into a discrete graph. In the general case, the graph is going to have weighted edges, and the different nodes in the graph are all of the possible states that our robot can get into in the world. So for a system like this, if we want to have a graph that's a perfect translation of this, this is a continuous space, so our graph is going to need to have an infinite number of vertices and edges, but we don't really need to search every single possible space. We don't need to, for example, for this car turning here, we don't have to consider every possible angle that the car can be at. We could, for example, limit it to be only whole degrees. So for every position that the car can be in, its tilt is going to be one of 360 possible angles. Similarly, we don't have to consider every possible position. Instead of that, we can make the position be to a resolution of 1 centimeter. So there's no option to move forward half a centimeter. There's an option to move forward 1 centimeter. And when we move forward 1 centimeter, the result is going to be at an angle limited to 1 degree. And that's still going to be, I mean, too many states. We're going to have to narrow it down a little bit more to actually compute it. But that description at least demonstrates that this is that this sort of infinite continuous space can conceptually be transformed into a finite discrete space. Once we have a finite discrete space, we can use a graph search algorithm on it, and that'll allow us to find a result. So let me pause this and go check whether this video works, and then we'll come back for part 2 if this plan actually works.